one thing your audience should know is that Brian and I have known each other for decades.
Mhm.
Brian actually took not one, but two classes from me back in the day. And it's great to have reconnected with him at Northeastern. So we go way, way back. And I think in the conversation today, you'll hear that our trajectories of seeing the planet change have gone on similar tracks and have caused similar angst in our lives. But we're both glass half full people. Just a quick note about what I do. I have been obsessed with the oceans since I was about 5 years old. And if I could, I'm just going to share a couple of heroes of mine of how I got obsessed with the ocean. So that's my dad on the left. And that's him going off to fight in World War II as a Marine in the Pacific. And when he was in the Pacific, he actually saw, speaking of frogmen, he actually saw the first frogmen that were used by the US Navy during World War II, in particular out in the Pacific Theater. And so when he came back from fighting, he was intrigued with the whole idea of a mask and a snorkel and fins. And those were actually consumer products that were just becoming available in the late 40s and early 50s. So he bought a pair of mask, fin, snorkel, and taught himself how to snorkel in lakes nearby, including the Great Lakes, where I grew up and he was born. And then the picture there shows a lake up in Ontario. And that's where he taught me how to snorkel when I was about 5 years old, was Lake Muskoka. And about that same time, the man who's wearing the red cap there captured the world imagination by bringing the undersea world to the masses. And Richard's got a strong story to share there too, having been a member of Team Cousteau in the early days. Well, you were still a teen, as I recall, Richard. Anyway, Jacques Cousteau started showing television shows on TV, and I would schedule my life around the latest episode, which usually came out about once every 3 to 6 months. So that's how I got interested in the undersea world. And I wanted to ask you, Brian, what was your trajectory to becoming obsessed with the oceans?
Yeah, it seems like you and I are on the same wavelength here. That's what I most often get asked during presentations like this. And so I've thought about it, how I ended up where I am, not only as a marine scientist, but also a climate scientist. And I think, talking to other people like you and other people in our profession, very, very few of us, when we were kids, said, I want to study climate. I want to be a climate scientist, especially those of us who, frankly, were looking for some way to get paid to go scuba diving. I mean, I think probably most of us at this call looked at marine biology as an excuse that someone's going to pay us to be underwater. And so I was, same thing, diehard Cousteau fan. I was looking for any way to work underwater. I got into this because I wanted to go diving and see stuff like this. And this actually is a picture taken at one of the places that Mark and I teach together in Panama, and taken by one of our students, our 3C students, Tim Briggs. But over and over again, we'd go to places like this, and we'd go back, and the next time we would see something that looked more like this. One of the things I'll say is it's kind of hard to not get depressed when you study impacts of things like climate change, as Mark will talk about microplastics in the ocean. But again and again, we'd see this in coral reefs. I worked in Belize. I would go down one year and it'd be this beautiful, lush coral reef, and we go down the next reef the next year and it's a parking lot. Same thing in intertidal systems. And so, once you start seeing enough stuff like this over time, you become a climate scientist just because you have no choice. but the other thing, and Mark, I think this is probably something you and I, we're also both goofy dads. I mean, probably the biggest influence on my career trajectory is my kids, right? I mean, these are my two daughters. This is how I will always imagine my daughters in my mind. My daughter on my left, this is a couple of years ago. She just started as a freshman at Northeastern this week. But as a father, I try to figure out how do you talk about this stuff in a way that's not depressing and ultimately is that glass half full that you're talking about. And so I started working a lot with their teachers. And so now I'd say about more than half of what I do is science communication rather than just the science. I think that I'd imagine that resonates with you as well, Mark.
Yes, I didn't start out to become a climate scientist. I wanted to be a marine biologist from age 6 onward. I do, though, shock my students that take oceanography now when I ask them, when we get into climate change science during the course, I ask this question, which amazes them. I say, what year did I give a 3-hour detailed lecture on the evidence for climate change and how it was already affecting greatly life in the oceans? And hands go up and people say, oh, 2007 or 2010. And their jaws drop when I say 1991.
Yeah.
So that's part of the failing of the science community, is that we talk to other scientists, we educate students, of course, but we didn't realize what was going on behind the scenes in terms of a massive misinformation campaign to deny the human influence in the distressing pictures that you just showed, Brian.
Yeah, and one of the things I always teach in my freshman classes is the same idea that climate change isn't something that we invented even in the 1990s. I mean, if you look back to the 1850s, calendar was doing these back of the envelope calculations of what the greenhouse effect was and what would happen if we just change it by a little bit. And the back of the envelope calculations are surprisingly close to what we get with these really fancy computer models now. So I mean, this is something that's been known since the Civil War. I mean, it's not something that we've invented or, that it's a
Chinese hoax.
Way of, Chinese hoax, exactly. I'm trying to figure out how to say this nicely, but yeah, I mean, this is something we've known about, and it's a natural process. It's just a natural process in steroids that is wrecking our planet. All right, and we're already starting to get depressing here, so let's so a little bit.
Trying to be glass half full rather than half empty. When we communicate science to the public, we do have to talk about things that can be done, and we'll try and mention some of those in our talk. One thing that I early on got interested in doing was trying to get a synoptic view of the ocean that has overcome a challenge that's been around since the time of the Challenger expedition, which was in the 1870s. So there was an expedition in the 1870s that circumnavigated the planet. It was the HMS Challenger. It was the first time that biologists, geologists, chemists, physicists, even artists all had to work together. They actually tore a ship apart. Let me see if I can find a picture of the ship here to make this possible. There's the crew that actually did that. That picture was taken in October 1874. And there's a picture, a drawing of the ship. There's a giant plankton net, which was an innovation that was new at the time in the lower right. But the upper left was a giant laboratory that they carved out of the inside of the ship. That was the first time that people from different disciplines were forced to work together in the same space. And it led to an amazing voyage of discovery. The volumes stretch across the width of my office. There was like 50 odd volumes that are still consulted today by marine scientists. That's how well done the work was. the Challenger expedition discovered that there was life in the deepest part of the ocean. They discovered that there was the world's largest mountain range was running between the continents, the mid-ocean ridge system. But when they did their science, they did it the way this little animation that's playing now shows what was done. And this led to about a quarter of the crew trying to mutiny, or run away whenever they made landfall. Was they'd move the ship and they'd lower instruments over the side, take a snapshot of what the ocean was doing, and then they'd move and do it again. And this was very tedious. So that sailing, stopping, dipping, repeating actually drove a lot of the crew mad. And that's a problem we still have in marine science, and that is that the ocean changes faster than we have the ability to observe. To make this intuitively understandable, if you look at that graph underneath the animation, the red line's going up and down. Let's pretend that's what the ocean is doing. And then let's pretend that we only have time and money to sample the ocean where those circles are. And once we get a bunch of data points from our expedition, what do? We do like a lot of the viewers have done who have been students or still are students. You draw a line between the points, and that leads to that blue curve there. And that's not what the ocean is doing. The ocean is going up and down very rapidly, but we don't have the ability to see that with approaches that we've used in the past. So what I wanted to show you was my attempt at trying to solve that Challenger style issue, and that is to have mobile sensors, underwater swimming vehicles, getting snapshots of the health of the ocean at a variety of scales, counting the fish in a certain area using video cameras or sonar, mapping the seafloor to look at changes like occur during coral bleaching, measuring the chemistry of the water. And so when we get those synoptic data, that we have a better handle on how fast these changes that are coming at us are occurring, and that will give us some management insights about what to do about it. So Brian, why don't you tell us about your related work in trying to get a synoptic view so you can make predictions about how fast the planet is changing with respect to, say, global warming.
Yeah, I mean, I think, as usual, you put your thumb on it here. What you're pointing out is a fundamental issue, not only with how we study the changing planet, but how we communicate it as well. And so it's been actually a uniting factor in the kind of two halves of my life, or the two halves of my lab, is figuring out at what scale do we talk about all this variability. Let me see if I can pull up the slides here. One of the hardest challenges we face in studying climate impacts and communicating it is figuring out how to use PowerPoint. Is the fact that we're talking about these large scale trends. I mean, it's by definition global climate change, and that makes perfect sense if you're a climate scientist. But if you're an organism or a normal human being, you could care less about what the 30-year trend is. What you care about is the local weather. I mean, the awful impacts of Dorian right now in the Bahamas ultimately are related to climate change, but it's playing out at that very local level. And so the challenge then is, how do we as scientists and then as a society take all this variability? I mean, as you're looking at this map right here, this is even variability in the trends, and there are places that are getting colder on the globe. There are places that are getting far warmer, like the Arctic. But the point is the total heat content of the globe is changing. So if you take the average of all these points, is undeniably been warming. But all that variability really matters because humans and other animals and other organisms care about weather. And so it's how that weather is affected by climate change. So, Mark, what you're alluding to, and for the rest of the people on the call, half my lab is trying to figure out, how do we communicate the links between weather and climate, and how we need to take a broader view than just our own backyard. but then the other half is saying, well, how do we use that information? How do we use science proactively to inform society? And so what we do is called ecological forecasting. And I was talking to a reporter a couple of years ago, and he really came up with this great analogy. And he said, well, really what you're doing is you are coming up on this big train wreck of climate change. When we're talking about mitigation, we're trying to slow down that train. We're trying to slow it down before everything wrecks. But in a lot of senses, we're already starting to see wrecks. And so if we're trying to deal with climate change, we're like EMTs coming up that have to put on toe tags. There are sites and there are species that, frankly, there is absolutely nothing we're going to do. If we waste all our money and political effort and resources on a site, and frankly, there are coral reefs like this, that there's nothing we can do, we're wasting those resources. Those are the black toe tags. There are places that are just like a patient that are doing fine. You keep an eye on them. Those are the places where we want to put marine protected areas. We want to have sites that are healthy now and healthy in the future. The ones that intellectually are the most interesting and the highest priority are those that are right in the middle, those yellow toe tags that if we expend a little bit of effort now, we can keep them from going over the edge. So, for example, we know that climate change interacts with things like pollution and runoff. By mitigating the non-climatic factors, we can help prevent some of the worst impacts of climate change. And so what my lab does in a nutshell is we try to figure out, we use satellite maps combined with detailed information on each of these different species to figure out where are those priority areas. How do we prioritize resources? How do we inform policymakers that, this is where they should expend the resources? And I think it all goes back to what you're talking about, Mark. It's recognizing that we're looking at a climate system, but ultimately that's playing out at very local scales.
Thank you for watching the Future Frogmen Conversation Series. Please check out our website at www.futurefrogmen.org.